And this also works, right? No, this doesn't work. This works.
Okay, so now everything seems settled. So we come to the last talk of this workshop. Speaker is Miguel Marques from the University of Halle, and he will talk about exchange correlation functionals for the band gaps of solids.
Hello, everybody. I'm really glad that you all had patience to stay here until the end. I will try to be as entertaining as possible because you must be very tired after this 2.5 days of very nice talks. I'm going to talk not so much about physics, actually. Most of the stuff I will talk about is about something that physicists hate, and that's statistics. Okay, so you'll have a lot of statistics and a lot of numbers, so it's kind of more chemistry than physics in this sense. And most of the talk will be about something that has been bugging me for a long, long time, and has to do with validation of theories. Okay? We are in physics is an empirical science, and we are all theorists. We all like the symmetry and the beauty and the exact conditions and all that stuff of our theories, but in the end, there is only one thing that really matters, and we have to be aware of that, is experiment. And that's what we have to compare to, right? And that's the final word. So I will talk a lot about density functional theory and functionals, especially for solids and then interfaces. And I will start by showing you a large benchmark of solids, for the band gap. That's the property I'll talk about here. It's I don't have to motivate why, I guess. You all know why it's important. And then if I have some time at the end, I will talk a little bit about some new functionals we developed to solve some of the problems that exist at the moment, okay? So we start at the beginning. We should always put a slide that everybody understands right at the beginning so that everybody feels that they are participating in the talk. So we start with density functional theory in general. So we all know this. We all know the Consham equations, right? This is already old, it's almost 70 years, right? And we also know that the Consham equations have this little term here, where we put everything that we don't know, right? The exchange correlation functional. Here it's the potential. You could also write it in terms of an energy. And this theory, I think it's actually the most useful theory in the whole of science in the last 70 years. And I can, maybe to be a little bit provocative, I can justify it. So first, why? And this is a citation from Axel Becker that says that DFT can be used to describe all of chemistry, biochemistry, biology, nanosystems, and materials. Well, to some extent, it's true. And that's the reason why it's so relevant. But this is, again, a theoretical explanation of why it is relevant. So I can give you a practical explanation. Nature, in 2014, made a list of the 100 most cited papers in the whole of science. And this is actually in the top 50, the articles that are related to DFT. There are 1, 2, 3, 4, 5, 6, 7, 8 articles related to DFT and DFT calculations in the 50 most cited articles in the whole science, not in physics. Okay? This is without comparison to any other theory in any other science. Actually, if you look, there is no update of this list, but if you did it now, I would guess that the top 50 has 10 papers on machine learning. That in 2014 there was 0. But now I'm pretty sure that in the 5 years, there must be at least 10 articles in the top 50 about machine learning, and the ones of the FT were reduced because they were. Anyway, now, when we do density functional theory for solids, we usually say, yeah, structures are good, but gaps are bad. This is what we have in mind, right? And this is what we have in mind. So we usually have in mind LDA or PBE gaps, and we know that if we plot the calculated gap as a function of the experimental gap, you get a very big underestimation of the gap. There are even theoretical reasons for that, right? Jean Perdue in 95 writes, even the exact Consham potential that generates the exact density generates a band structure which underestimates the band gap. This is true. We know that in exact DFT, the band gap, the Consham band gap has to be smaller because there is the derivative discontinuity that is missing. However, we also now know, and this is again Jean Perdue in 2017, that in generalized Consham theory, that means the thing that you're actually solving when you do meta-GGAs or hybrid functionals, the band gap equals the fundamental gap. So maybe it's not as bad as we thought, okay? So there is hope that we can get from DFT the band gap, and we don't have to do these costly many-body methods with all these hundreds of different versions. How can we know how bad it is, actually? I only know one way, and that's to compare to experiment. And this has obviously been done many times. But if you go through the literature, you find that all the benchmarks and all the comparisons have been done in rather small data sets. And this is a curse that we have in physics in particular. It's the curse of the small data sets. So most papers compare to 20, 30, maybe 50 materials. And if I ask you which materials are these 50, you can probably guess them, because they are mostly SP semiconductors that are used in electronics. They're all zinc, probably 70 or 80% of them are zinc blende or wurtzite. And if you ask someone that does statistics what he thinks about this, he will say this is statistically insignificant. You cannot make any statistic, you cannot extract any statistic conclusion from such data sets because they're extremely biased. So we have been developing theories and theories and theories, and functionals that are around 500 that I know of, 600 maybe. And we are basing all our conclusions on completely biased data sets. This is not generally true. There are some properties that are much better studied than others, but for band gaps, this is actually true. So we said, let's try to find the largest data set that we can obtain, experimental data set. And I was naive at the beginning. I thought I could find thousands of semiconductors. And then we come to the hard reality of the literature. Experimentalists don't do systematic work anymore. So they don't. You cannot get a Nature or a Science by doing systematic work. So no one does it anymore. It stopped in the 70s and the 80s. It stopped. So if you go through the literature, you can find around 500 band gaps that you can use. And then you say, 500 is a lot. No, it's not a lot if you compare to all possible materials that you know. We have 100 elements, right? So 500 with 100 elements is already not so large. But then you look at the separation of these materials by element, and you realize that most of them are oxides, sulfides, and selenides. Okay, so even these 500 are extremely biased. Extremely biased, but this is what we have. Then, so this is what we can find. We spent several months analyzing the literature and going through experimental paper after experimental paper, and we cannot really find more that are usable, okay? So we have these ones. We have most chemical elements represented, okay? We have a large distribution of band gaps of semiconductors, so they go basically from 0 to 20-something eV, of course. There are van der Waals, ionic, and covalent materials. Of course, I can also not distinguish so well between what are, I mean, there are, of course, some paradigms for each one of them, but most systems are in between. We removed all magnetic systems because most semiconductors that are magnetic are antiferromagnetic. And then you have the complication of also finding the antiferromagnetic cells. So to avoid complications, we remove magnetic systems. And we have up to 32 atoms in the unit cell. Okay? Of course, before talking about this, these are experimental numbers. And now you're going to tell me, yeah, there are a lot of problems with experimental numbers. And it's true. First of all, most papers, experimental papers, don't even give the temperature of the measurement. This was a very big surprise for me. But in more than half the papers, we don't even know at which temperature it was measured. Second, most of the measurements are optical. This means they are obtaining optical band gaps, so we don't know the excitonic binding energy. That's already the problem. But one gets the band gaps by extrapolating a plot. Extrapolation of a plot has an error, so you'd expect that you'd get band gaps with error bars. There's not a single experimental paper out of these 500 that actually show what is the error in the fit. Okay? This was a very big surprise for me. So we don't know the temperature, so we cannot correct for the temperature because we know that the band gap changes. We don't know the exciton. We don't know the accuracy of the experiment. And of course, there is still the 0-point energy, right? That is even worse. So we have here a series of problems already from the experiment. So each one of these probably gives you errors of the, if you have a gap of 2 or 3 V, will probably give you 0.1, 0.2, 0.3. On average, it will be 0 point something eV. It's hard to quantify, but let's keep in mind that we have already these 4 things that we don't really have to control. If you want really well-defined experiments, then you cannot use 500 materials. You'll use 20. And then we go back to the same problem that your theories are tested in a completely biased set. So you cannot conclude anything. So here we have the hope at least that some of the errors will compensate, and statistically we can still conclude something. Okay? Now, to run the benchmark. It's very simple, very straightforward. Any one of you can do it. You don't have to be a genius to do this, certainly. We did VASP, and we modified it to use libxc, so it was not a very big modification. Actually, in principle, version 6 of VASP, when it comes out, it will have already libxc, so you can run all these things yourself. And we tested basically all the functionals that had something to do with band gaps, okay, plus some commonly used functionals. So there are LDAs, there are the orange ones. Yes, there is more than one LDA. Several GGAs, several meta-GGAs that are now the very active field of development also for band gaps, and some hybrid functionals that's what within DFT you would consider state-of-the-art to calculate calculate band gaps. So most people would say that they will use either an HSE calculation, so a screened hybrid, or a PB0. There are many, many articles using this also, okay? So the question is, how does this work, okay? So in principle, with these 2 here, with the orange and the blue, you should get band gaps, because this is pure DFT. With this, which color is this actually? Pink? I don't know. Magenta, okay. And green, you could have, theoretically speaking, good band gaps if you care about purity of theory, okay? So first, some details. Let's start about pseudopotentials. I use pseudopotentials, of course. We use VASP, so they are PAW setups. And from many, many years ago, I remember hearing over and over again that you should do the calculation with the right pseudopotential. So if you do a PB calculation, you should have a PB pseudopotential. However, in 2020 now, we are in a situation where to calculate band structures, we typically use hybrid functionals or GW. I don't think there is 99% of the calculations done in this way, they are done with the wrong pseudopotentials. Because you don't have pseudopotentials for hybrid functionals, you don't have pseudopotentials for GW. Okay? So it's important to quantify this error. I didn't know how much this error was. I mean, I asked around, people said, I don't know, it's probably okay. So let's quantify it, okay? This is a GGA calculation, but with a functional that actually gives band gaps. You will see afterwards that gives band gaps that are in agreement with more or less in agreement with the experiment. And we tried a couple of other things, and this is more or less consistent. So I think the error will be of this order of magnitude also for GW or hybrid functionals. So we compare to Vin2K. We would expect at least for a GGA, Vin2K will give you the right answer. Let's assume so. It's a LAPW. And this is what you get. So this is the band gap in VASP with the pseudopotentials, in this case a PAW setup. This is Vin2K. And it's not too bad. Yeah? The average error is 5%. So keep in mind then that if you see a hybrid calculation or a GW calculation or anything like, or a modified Beckett-Johnson calculation, that we'll talk about it, we already start by having an error that is likely of the order of 5% on average. Unfortunately, the problem is not the average. The problem are these points here. You can have errors of the order of 30% of the band gap by using the wrong pseudopotential. And this is an urgent problem that we have to solve. For some functionals, it's easy to solve. For GW, I don't really know how to do GW pseudopotentials, so I don't know. LAPW with GW has other problems, so I don't know if there's a simple solution to this problem, okay? But keep in mind this number, 5%, okay? This is the error that we have from pseudopotential, so 0.1 EV is the average error. So again, it's the same order of magnitude as phonons, as temperature effects, as excitonic effects, more or less the same order of magnitude, okay? Then we have relativistic effects, right? We cannot forget spin-orbit coupling. So we also tried that a few functionals with and without spin-orbit coupling. The mean error is again of this order of magnitude, 0. So mean error means the difference from the calculation with spin-orbit coupling and without spin-orbit coupling. We again go into the 0 point something EV, okay? Actually, gaps, of course, with spin-orbit coupling are closer to experiment, which is really reassuring. But the difference is not gigantic, okay? This is orders of magnitude, and you will see the numbers themselves. On average, spin-orbit coupling is small, of course, because on average, I told you we have oxides, sulfides, and mostly they are oxygen and sulfur are small atoms, so it's not a problem. For some individual cases, results can change a lot. So the error, the maximum difference is 1.3 eV. And to our surprise, this can change a lot if you change functional. So it's not true that you can just grab spin-orbit coupling calculated at PBE and add it to GW. This is not true at all. Okay? It might if you're lucky, but I'm never lucky. So, so this is the summary of the benchmark. Okay? This is a little bit complicated. Let me try to guide you through. This is the mean absolute percentage error. Let's take this as it's a statistical measurement. This is probably better for large band gaps than for small band gaps, but it's a statistical measure. This is the mean absolute error. And here are all the functionals. Again, the colors are the same as before. We would expect from this wonderful image of the Jacob's ladder that the worst would be LDAs, then we get GGAs, then you'd have meta-GGAs, and then you'd have hybrid functionals, right? This is the order of the rungs in Jacob's ladder. So you'd expect that if you go up the Jacob's ladder, the results, the functionals would get closer here. Well, this is obviously not the case at all. Okay? It doesn't really matter. You can get good and bad results with any kind of functional, for band gaps in this case, of course. LDA is here. It's pretty bad, as you know, errors of around 50%. What you don't have plotted here is actually PB0 that so many people use for band gaps because it's outside the plot. It's somewhere here. PB0 was the worst functional we tested. The errors are 65%, the average error. So if you want to do a calculation of a band gap, I strongly suggest that you don't use PB0 unless you already know the answer. And if you already know the answer, maybe PB0 is your best functional. But if you don't know, you're better doing LDA. The best things are here, okay? The two best functionals are undoubtedly the modified Beckett-Johnson. This is a very simple and ill-justified, I would say, meta-GGA that has a lot of problems because you cannot use it, for example, for anything with reduced dimensionality. It's not size consistent. It's all the things that you may imagine are wrong, but it gives excellent gaps. It's the best by far, and this is confirmed by other benchmarks, not only us, okay? And then you do have a hybrid functional that is HSC06, the screened hybrid. That's okay. Okay, that's pretty okay. Of course, this takes much longer than this, okay? So if you want just a band gap, you can do an HSC calculation, but it's not worth it, right? It will take you 100 times longer. If you want, you can do it. But if you just want a band gap, you shouldn't do it. Just do modified Beckett-Johnson. These are some new, this is a new meta-GGA from Stefan Kümmel that actually came out just a couple of months ago. That is also not so bad. And there are here a couple of relatively empirical functionals from Don Trular. Very, very simple functionals that actually converge very well in contrast to the modified Beckett-Johnson. So this, I would say, it's also a good choice. This is an LDA. This slok is an LDA. So we can get more or less, you see, there are differences, the results are not so different. You go from 30 to 35%, from 0.5 mean absolute error to 0.7. So it's not too bad. So you can get actually good results with an LDA. I never thought this was possible. So to show a little bit better the individual functionals, I will show you what we call what is called radar plots. So you cannot really look at just one statistical quantity because again you may be looking at the wrong thing. This is just a plot where in each axis you put a different statistical measure. Okay? The closer you are to 0, the better, the better it is. So you'll have here the mean absolute percentage error, the mean percentage error, and so on and so forth. There's a series of statistical measures that it's not important here. And you have here the best functionals. So the best LDA, the best GGA, the best meta-GGA, and the best hybrid. And you can clearly see from here that in all statistical measures, clearly the modified Becker-Johnson is the best, okay? Considerably better than a hybrid, than the HIC, than the best hybrid that is here. These are not so bad either, okay? These are not so bad either. Now, we have all this data, and so we asked the stupid question, can we do what chemists like to do? That means optimize functionals. We can train. I mean, we have 500. To train standard functionals is enough, maybe not to do machine learning, then we'll come to that later. But to train, to fit a couple of parameters is clearly enough. So we did that. So we just varied the internal parameters of the functionals and calculated and optimized them, okay? We had in the end, we had plots like this. So for example, this is PBE. This is the two parameters of the exchange in the PBE. So this is to obey the Lieb-Oxford bound. This is the semi-classical coefficient. And this is the error here. So the mean absolute percentage error of this functional with these two parameters. And so what is rather is better. These are the typical. These are 3 PBE-like functionals. There are at least 10 different versions of the PBE that were proposed already. It's a very ab initio functional, but there are at least half a dozen theoretical justifications for 6 sets of parameters. But this is the minimum we get. We get another minimum around here. Okay? So you can actually get good gaps with the PBE with 2 completely different sets of parameters that have nothing to do. They give very different results for each individual solid, but on average, the error is more or less the same. So we try to do it for LDA, for the PBE, for this high local exchange. GGA actually should be 16, but doesn't matter. And for some meta GGAs, okay? And here it's again the summary of what you get. And so the PBE was here. For example, the optimized PBEs, they end up here. So I think the main message is that you can get good gaps with whatever you want. There is no problem. You don't need to do sophisticated theories, okay? But there is a limit. We cannot pass around 30% of mean absolute percentage error. We did not manage. Whatever form you use, you're always kind of stuck there, okay? Now, it's not clear if it's the quality of the experimental results. It could be, right? Or all these phonons, temperature effects, excitonic effects that pollute the experimental data, that it's not so easy to correct for, especially for 500 materials. But it seems that we are stuck there, okay? Can we do better? Well, let's go to everybody's favorite topic nowadays, right? Can we do machine learning? In fact, I think last year or 2 years ago, there was a paper doing machine learning, what we call component prediction. So that means given a certain composition to predict the gap of this composition. And they used, they have more than 500 band gaps because they can take alloys and they can take also materials for which we don't know the phase that was measured because they only have the stoichiometry, the composition, so that is fine. And we have a lot of experimental data on phases that we don't know what they are, which is also quite amusing, but there are many papers like that. And they were partially successful, I would say, even if for them, graphite and diamond have the same band gap, because, of course, it's just composition, band gap to relationship. So we thought, can we do something a little bit better? So we have a lot of results. We had 50 functionals or so. Can we use, in particular, the results from these 50 functionals and improve them using machine learning to get closer to experiment? Now, you probably know that from machine learning is a data-driven approach. So you need data. And when we talk about data, we don't talk about 500 numbers. We need 50,000 numbers, okay? The orders of magnitude are totally wrong in physics. We don't have data, experimental data for almost anything, okay, in physics. In chemistry, it's a bit different. So it's very hard to do machine learning based on experiment. What you can do is simple machine learning. So you do very simple models. Okay, and this is what we tried. We tried this model agnostic supervised local explanations. It's tree-based, and it gives you very simple models that you can actually interpret. They're very, very simple models. And as input, we used the band gaps that we calculated, hoping that they were good estimators of the actual band gap. Yeah. And then we added other stuff like chemical composition, symmetry group, whatever. And this is what we got. So let me see. This here, the orange one, is the original modified Becker-Johnson. So that's our best functional, okay? This is what you get by using different machine learning models. So you see, some statistical measures you improve, but mean absolute percentage error, that is probably the thing we'd like to improve the most, we cannot. We don't have enough data. There is no way. I think we can forget it. There is not enough experimental data to do any machine learning. We have 100 elements, 500 materials is not enough. So then we thought, can we actually do something to, to sort it out? And we found out that if you actually restrict your set to the place where we have the most experimental data, that is around between 1 and 2 eV. And this is fortunately also what you need for photovoltaics, for example, right? This is you get this, and then you see you go from this, that is the original modified Becker-Johnson, and you can actually decrease the errors by a factor of 2. Little problem, in order to use this model, you have to know that the experimental gap is between 1 and 2. It's not that the PB gap is between 1 and 2. It's that the experimental gap is between 1 and 2, okay? Which is a little bit worrying because you don't know. If you try to predict it, you go back to the original error. It's a little bit depressing, okay? So I don't have time, I think, to go through everything else. Let's just say that the two best functionals, unfortunately, also have problems, okay? And we are working to solve them. So the hybrid, has the problem that has a constant mixing and constant range separation for all materials. And this is clearly not physical, and this is clearly not correct. Okay, and we worked a lot we and other groups to solve these problems. And then because of this, it also fails for large band gap insulators. It really gives very, very bad results for large band gap insulators. And then the modified Becker-Johnson that I was selling here as the best function to calculate band gaps involves an integral over the unit cell. So if you don't have a unit cell, if the system is not periodic, you cannot define it even, okay? So there is no way of doing pseudo-potentials with modified Becker-Johnson because you cannot run it for an atom. And so we go back to our problem from the beginning. So it is ill-defined for low-dimensional systems, and we work on solving this problem by localizing things. I really don't have time. I don't want to go through this. I just wanted to show this. We made a local version of the modified Becker-Johnson. Actually, it's work from Thomas that had a poster. I don't know if you saw it about it. And the basic idea is to go from all these integrals over the unit cell to local quantities, and then you can generalize this functional, and it works for, let's say, finite systems, surfaces, and it gives the same thing for solids, and it at least can be used for other things, okay? So I don't have time for these things, so it doesn't really matter. So concluding, we have a data set, small data set of 500 materials. It's at least a factor of 5 larger than all the other ones until now. It's still too small, but I don't think with the current status of experimental research, we will be able to expand it further. Of course, you can find 400 experiments that measure the band gap of methyl ammonium lead iodide. That's very, very well known, but I don't care about 500 measurements of the same number. So the best functionals are clearly the modified Becker-Johnson, and HSC06 is, I think, is the message. There's a huge problem with the data that I don't know how to solve. And the problem is that there are 4 or 5 things, and they're all more or less the same order of magnitude, and it doesn't make sense to improve one without improving the other ones. I mean, unfortunately, I think this is the case. And we do have, so for these 2 functions that are the best, we do have improved versions. that allow to solve some of the problems of these functionals. Yeah. So I would like to thank everybody that worked on this. Of course, my group in Halle, the group of Silvana, especially Thomas, that worked on the modified Becker-Johnson. And this is a collaboration with Fabian Tran in the Vienna that did all the VN2K calculations and provides us benchmark data with what LAPW can do. Okay, thank you to all of you. And
thank you, Miguel. Many questions?
Yeah. Very nice talk. One question, what about other properties, distances, or do you think that the benchmark will turn out similar?
No. Yes and no. For structural properties of solids, we do have enough data. There is no problem. ICST has 50,000 crystal structures that you cannot use all of them, but you can use many of them. Unfortunately for solids, and this is really interesting, only lattice parameters have been tested. I don't know any benchmark that actually looked at internal coordinates. But we do have chemistry that looks at coordinates, so that's probably okay. And that we know, for example, that the best GGA functions are PB Sol and AM05. So it's really funny that most people still use the PB to optimize geometries when we know that there are functions that are clearly better and that cost the same. Other things, for example, formation energies, for me, it's the worst. There are 250 formation energies in the literature, experimental formation energies in the literature. There are 100 elements. People have been doing machine learning or improved theories to get formation energies, but what do you do with 250 numbers? And these numbers are actually of low quality. Experimentally, they have very big errors. So I feel a bit frustrated because the more you search the experimental literature, the more you realize that it's useless to do theory because you cannot validate your theories after a certain level, of course, right? This is what I mean. Don't take me wrong. I'm not saying that all we do is nonsense, not at all. It's just that we have reached a level of precision that if we want to go beyond it, we need high-quality experimental data, and we don't have it. So it depends on the property.
Yes, a related but different question. In your simulation, it was very interesting, actually, very. In your simulation, you start from a geometry, including parameter, internal parameter, and
experimental geometries.
You took experimental lattice parameters and internal coordinates.
So most of these structures are actually what the ICST calls them high quality, okay. Even if we did find a couple of problems.
Okay, so you consider that for most of material you have exactly the same geometry in experiment and what
so one of the conditions we put, besides that you did not have more than 32 atoms in the unit cell, which is already much more than what most people take in any benchmark, right? Yeah. Because usually take 4 was that there was a ICST, well-defined ICST structure and a well-defined structure in the materials project that we were kind of sure that if you'd optimize the experimental structure, you didn't end up in something completely different. Because this does happen. X-ray data is not always obvious to analyze, as you know. And so these are the materials for which you have a band gap that was not obviously wrong from the experimental literature, and that the structure looked okay.
Okay, so one question here.
So increasing the statistics is good only if you get uncorrelated stuff.
Yeah.
And now you actually have all the tools to say if the Schilfgaard-Kottani set of 30 materials is actually representative or not.
It is not. It is not.
Why?
Because if you apply this so we didn't try with the one of Schilfgaard and Kottani, and we did try with a set of 76 materials that was used by Fabian Tran in a previous paper, and the errors go from 30% to 15% in some functionals. For some other functionals, they remain constant, but for others, you go errors that you can get very reduced errors. And this can mean only two things. Either that the 76 materials that includes all the zinc blend and all the wurtzite that you know, plus a couple of oxides that we take as oxides, even if oxides are extremely varied. Either this is highly correlated, or the experimental band gaps that I have for the other 400 materials is very wrong.
No, I don't know about the trans sector, but you know, the Schilfgaarde one spans quite a lot of classes of bonding, and that's why, you know, it goes up to rare gas solids.
So typically, yeah, you get rare gas solids. There are four, typically, right? Helium, neon, argon, krypton. Then you get some ionic compounds. So you will go to the lithium fluoride and to the sodium chloride, always in the rock salt structure. And then you get SP materials. That will be your gallium arsenides, your silicons, your diamonds, and so on and so forth. And then typically you add a few oxides. You usually don't put any fluorides or chlorides besides the really very, very ionic ones. And you usually don't have anything that has mixed valence, nothing with more than one cation. So I would say they're not representative at all.
Well, I think one can make a numerical statement of this.
One cannot, because the sets are so small, even this one. I think all these statistical statements have so much imprecision. Maybe. I'm not saying you cannot, but maybe.
Over there.
Okay, very impressive data set. At the beginning of the talk, we saw some word LIBXC.
Some what, sorry?
LIBXC.
LIBXC, yes.
What is that? Can you please?
That's a library of exchange correlation functions I've been developing for like 20 years. And that is has around 500 functionals by now. And this is by now used in almost 40 codes. So you can in many of these codes, you can just use any of these 500 functionals. VASP did not have an interface, so I wrote one. And so that's LibXC. It's available, it's open source. So.
Okay, thank you.
But I mean,
and maybe one quick question, because if you remember that you have meta-GGA, you have short range corrected HSA06. However, do you believe that long range corrected sum functional to be included? Because I'm not surprised that your tool is applied for 1 or 2 EV bandgap solids, which is basically your HSE, which is short range corrected functional. But what would you expect if you include a long range?
Long range
correctors.
Long range character
on the exchange correlation.
So the other way around, you go to a long range corrected functional instead of going to a short range corrected.
I mean, alone with short range.
Sorry?
Alone with short range corrected functional. So what will be the additional point in your plot?
I mean, all this, let me be very blunt. All these hybrids are very basic in a way. These parameters are very straightforward, understood in terms of physics. I see them in terms of screening, okay? And then you will see that whatever simple approximation you make to range separation or to mixing or whatever, and short range, long range, this will mean that you're either describing, well, large bandgap materials or small bandgap materials, or if you want to compromise, medium bandgap materials. If you want something that works everywhere, and that's the problem of PB0, right? It works well in a very narrow range of materials, and you'll get B3-LIP will work also in another range of materials. So you will have to do something more complicated, I think.
Thank you.
Can you give the microphone to Max, who's just...
So you haven't said anything about it. I just read these couple of these words in one of your slides that for inhomogeneous systems, you need to calculate the local dielectric function. I wonder if you could say something about it. I was curious what you mean by local dielectric function and how you get it.
I think we all agree that if you do, if you have highly inhomogeneous systems, the dielectric function will be highly inhomogeneous also, right? If you take a hybrid or actually this modified Becker-Johnson, the idea, the C that they have is kind of related also to a mixing in a way. The mixing is related to a dielectric constant. And if the system is homogeneous, yeah, the electric function is a number. If the system is homogeneous, it's not a number, right? So if you want to describe properly in a homogeneous system, and even if just a surface, your mixing should depend on space in some way, right? So what we did in this case was obviously not calculated the electric constant. There are many people doing it. I mean, you know, people have anyway been doing screen exchange for 30 years, which boils down to that. But what we did was actually get an estimator of the electric constant in terms of the density and make it local, in the semi-local, in the sense that to define a band structure, you don't need the whole material, right? You just need a range, because many things are rather local, and with semi-local information, well, semi-local, it's non-local, but in a range, you can get an estimation of the screening properties in that area and use it to make a model of a local, even a rather non-local mixing that is related to the inverse electric function. I can explain you better if you want what I mean. Okay. Yeah, but I think it's clear that if the material is homogeneous, just using one number for something that has the meaning of an inverse screening, it will not work.
Right. Okay. So you don't calculate actually the response function.
No. Some people do it, yeah, sure, okay. But it's something you don't want to do because it takes time. Yeah. It takes time. So what we did was try to find an estimator for that based on the density functional electric constant.
Okay.
Okay. So we have one last question here from the back.
Thank you for the very nice talk. I have just one question. So you said that indeed experimental data can be also a bit misleading to compare with, because you know there are no electron phonon coupling and effects that even if our function is perfect, we expect not to reproduce exactly the experimental band gap, and then there are all these problems about the uncertainty. Why isn't maybe better to choose some golden theoretical method to benchmark with DFT kind of?
That's easy for molecules. I don't know what is the golden method for solids, because you cannot really do couple cluster precise. You cannot do full CI. Monte Carlo has the promise of doing it, but if you look in the literature, there are not so many Monte Carlo calculations for solids that you can use. So what do you use? Yeah, that's a big problem. It's also a problem for machine learning. You want to do machine learning. You will fit it to what? For solids. That's an answer. That's a question that I haven't seen answered. You don't know. For molecules, it's easy. It's relatively easy. We know what to do, right? You can do full CI for small molecules or a couple cluster, or even now the Monte Carlo with machine learning, and you have a golden standard without any of the extra complications of experiment. But for solid, I don't know. We have the electron gas.
Okay. So
doesn't have a gap, the electron gas, so it's a little bit.
So let's thank again, because I think no one knows an answer to this final question.
I hope I was entertaining enough.
In fact, I think it is very nice to finish this workshop on this kind of very note which goes to the basis of what we are all doing all the time, and going back to looking at our tools and how reliable they are in the end. Be careful, because you have...
that's the problem.
Okay, so thank you very much. Thank all the speakers of today again. And I think now we have some concluding remarks, I imagine, by Ivo.
Yes, very quickly, because people have to catch planes and all that. But I would like to thank all of you for coming here, participate, and in particular all the speakers for, I think I speak in name of everybody in saying that they were really very stimulating, and they displayed the breadth and the depth of the research in our community. And as we close this event, it's a good time to look ahead and think of the next event in this series. And since one of the organizers of the next Total Energy Workshop, Nicola Seriani, is here, we take the opportunity to introduce him and the workshop.
Thank you very much. I'm Nicola Seriani from the ACTP, and as you know, next year, as usual, the Maxi Total Energy Workshop will take place there. And I see the organizer have not made it easy for me, for us, because by keeping the bar of quality very, very high. So we hope to stand up to that challenge. And we have an organizing committee composed by myself, Mauri from the University of Rome La Sapienza, from Silke Birman, from École Polytechnique, and from Tanusri Sahadas Gupta from the Bose National Center for Basic Sciences in Kolkata, India. And we are looking forward to see you all in Trieste in January 2021. So thank you very much.
Great. And maybe we also take the opportunity to remind you again of the other big event in our community this year, which is organized by the other Nicole in the room. So,
thank you, Ivo. I didn't expect this, but yeah, as mentioned, Psyche 2020 will be in Lausanne from 14th of September. It's a Monday, starting just after lunch to Thursday 17 until the evening. And then there will be a disco event for which I've been working on the music selection for the past few months. And I'll keep working until the very day.
Okay. Great. Yes, I think it's 70s music, right? So great. Okay, so that's it. And I wish you a safe trip back home. And thank you very much for having come to San Sebastian. And see you at some other event. Bye-bye.